AC circuit analysis using complex variables is a fundamental topic in electrical engineering and electronics. Let's break down each of the scenarios you mentioned. A. Capacitance and resistance. In an AC circuit with capacitance, C, and resistance, R, you can analyze it using complex impedance, Z. The impedance Z in this case is given by Z equals R minus J, 1 omega C, where RR is the resistance in ohms, ohm symbol. CC is the capacitance in farads, F. Omega is the angular frequency in radians per second, given by omega equals 2 pi f omega equals 2 pi f, where FF is the frequency in Hertz HC. The magnitude of the impedance, Z divides, represents the overall opposition to the flow of AC current, and its phase angle, theta, represents the phase relationship between current and voltage. B. Resistance and inductance. In an AC circuit with resistance, R, and inductance, L, the impedance Z is given by Z equals R plus J omega, where RR is the resistance in ohms, ohm symbol. LL is the inductance in henries, H. Omega is the angular frequency as defined above. Again, you can calculate the magnitude, Z divides, and phase angle, theta, of the impedance. C. Capacitance and inductance. In an AC circuit with capacitance, C, and inductance, L, the impedance Z is given by Z equals J, omega L minus 1 omega C, where LL is the inductance in henries, H. CC is the capacitance in farads, F. Omega is the angular frequency as defined above. You can calculate the magnitude, Z divides, and phase angle, theta, of the impedance. D. Capacitance, inductance, and resistance series and parallel resonant circuit. When you have a series or parallel resonant circuit consisting of capacitance, inductance, and resistance, you need to consider the specific configuration, series or parallel, to determine the impedance characteristics. For series resonance, the impedance of the circuit becomes minimum, and the circuit becomes purely resistive at the resonant frequency. The quality factor, Q, can be calculated as Q equals omega 0 L/R, where omega 0 is the resonant angular frequency. For parallel resonance, the impedance becomes maximum at the resonant frequency. The quality factor, Q, in this case can be calculated as Q equals R/omega 0 L, where omega 0 is the resonant angular frequency. The quality factor, Q, is a measure of the sharpness of resonance in the circuit. Higher Q values indicate a narrower bandwidth and a sharper resonance peak. In all these cases, complex variable techniques are used to analyze the impedance and phase relationships in AC circuits, which are crucial for understanding circuit behavior in alternating current applications.